name is Jacob Hickman, and this is my video presentation of the 3 extra credit problems for probability in simulation in MATLAB programming. I'd like to get right into it. This is just some of the stuff from Lab 3, but we get down here to the first problem, the movie theater. What we have here is a situation where people are going to be lining up, 200 of them, some paying with a $5 bill and some paying with a $10 bill. So what I'm going to run is some cases where I'm going to just do 1,000 iterations where 200 people line up here and they have a random chance. This Randy integer is going to either throw up a 1 or a 2. So if it happens to be a 1, that means I'm going to consider them that they paid with a $5 bill. So we add $5 to register, and if it randomly gets a 2, then you're going to pay with a $10 bill. So we need to refund them $5. We're going to keep track of that, and we're going to run how many $5 bills the cashier has in his register, starting at 0 and running up to 30 $5 bills. So any number from 0 to $150 in $5 bills, so we can see what kind of percentages he's going to do and if he'll make it, if he'll have enough change. So for every time that he runs out of money, we're going to track a failure here, and we're going to use that failure to determine our percentage chance of success at each dollar amount. So let's run that cell, and it's just going to plot it. When the cashier has $0, there is a 5.6% chance of having enough change. And as this would make sense, the more money he has in his drawer, the higher the percentage chance that he's going to make it through all 200 customers. So through experience, I knew that he would stop at about 150, would be more than enough, but we can see the criteria was, when does the cashier have a 95% chance of making it, and it's right here. When the cashier has $135 in $5 bills, he'll have a 95.4% chance of having enough change. So that solves that problem. The next problem is a printer collision. So this one's an interesting one. There's two printers that can request their documents to be printed at any moment. So I considered that to be 3,600 moments in an hour. And if the printing job starts, it lasts 20 minutes. So the most that it can delay the other printer is 20 minutes. So we need to see how long the average wait time is for these computers. If one gets there first, the other one will have to wait. So it's pretty interesting. A lot of if statements is basically how you did this with some random numbers again. Basically you're making a random call. It's going to hit at this S, so 3,600 seconds in an hour, and you're going to pick a random number for printer 1 and a random number for printer 2. If in the really crazy circumstance that they both pick the same random number, there's a collision, and that will be an interesting little statistic to calculate as well, but most likely one is going to be slower than the other. So if P1 is slower than P2, or if it comes before P2 basically, then this printer 2 is going to have a delay, and it'll start once printer 1 is done. And then the rest of this is just adding up the waiting time, how many collisions it has, and then we're going to get our mean waiting time in minutes and the percentage chance of a collision. So let's run this cell, and we're doing 100,000 iterations right now, but it gives us a pretty good idea. And it just says that the computers will clash at the printer 0.025% of the time. The average waiting time is 559 seconds, or 9.32 minutes. If we do that again, it'll change it slightly, 9.31 minutes, 9.34 minutes, etc. If I add a 0 to that, make it a little bit more accurate, we'll run a million iterations. It takes a second longer. There we go, 9.33 with a 0.027% chance of a crash in those 3,600 seconds. Alright, and then the ducks of the feather problem is the last one. This is a situation where there's 6 hunters and 6 ducks. Each hunter takes a shot, and he's going to kill the duck that he hits, no matter what, but there's the chance that 2 hunters could hit the same duck, so there is a chance that some of the 6 ducks will survive. So So basically I have hunter 1 through 6 getting a random number 1 through 6. And then there's these situations where if hunter 1 random number comes up to a 1, then duck 1 is dead. If it comes up to number 2, then duck 2 is dead, etc. And then we repeat that. I'm sure there's a more eloquent way to do this coding, but this is all I can figure out. So anyways, we go through all 6 hunters with all the chances of hitting it. And then this is just the little part where you can't kill the duck more than once. So we're going to count up. This is going to reset D1 to 1 every time, even if hunter 5 and hunter 6 kill duck 1, we're still just going to count it a 1. So we add up the number of hits. So say 4 ducks would hit, this would come up to 4, and then we're going to divide that by the total number of shots taken, and then the number of shots taken divided by how many iterations we're going to run this, and that will give us through here what kind of percentages these survival rate of these ducks. So we run that. It says that the research duck will survive 33.49% of the time, 2 ducks should expect it to survive, and basically 4 ducks will be served for dinner. So that will finish that one up. If we run it again, it says the same thing, pretty close. So 2 and 4, that's the answer, 33% of the time.